Hello friends, welcome to this lecture. In this lecture we will continue our study of say stability of nonlinear system. So, if you recall in previous class we are discussing the following following system of differential equation, that is x dash equal to Ax plus Gx, where x is n cross 1 vector and A is n cross n matrix and G is the n cross 1 matrix function. It is given as Gx equal to G1 x to Gnx, and here we have we are assuming that the nonlinearity given by the function g of x is say is small compared to the linear part, that is A of x. So, here we have assumed that Gx is a function such that Gx divided by norm of x is basically Gix divided by norm of x are continuous function of x1 to xn and vanishes for x1 to xn equal to 0. So, here by putting this condition that g of x equal to 0 for for x equal to 0 simply says that x equal to 0 is a an equilibrium solution of the system 1. And here and we call this kind of a system as weakly nonlinear system, and we have discussed we have started proving the theorem number 1, which says that suppose that the vector valued function Gx by norm of x is a continuous function of x1 to xn which vanishes for x equal to 0, then the part A, that the equilibrium solution xt ideally equal to 0 of 1 is asymptotically stable if the equilibrium solution of xt ideally equal to 0 of the linearized equation, that is dx by dt equal to Ax is asymptotically stable. And we have already seen that the system of linear equation dx by dt equal to Ax, every solution of this will be asymptotically stable provided that all the eigenvalues of A have negative real part. So, it means we can say that if we summarize these two facts, then we can say that the equilibrium solution xt ideally equal to 0 of 1 is asymptotically stable if all the eigenvalues of A have negative real part. So, and the part B says that the equilibrium solution xt ideally equal to 0 of 1 is unstable if at least one eigenvalue of A have positive real part. So, this is the B part, and C part is that the stability of the equilibrium solution xt ideally equal to 0 of 1 cannot be determined from the stability of the equilibrium solution xt equal to 0 of dx by dt if all the eigenvalues of A have real part less than or equal to 0, but at least one eigenvalue of A has 0 real part. And in last lecture we have discussed say two example based on the part C. In fact, we started with the part C and we have shown that in this part when dx1 by dt equal to x2 minus x1 into x1 square plus x2 square and dx2 by dt equal to minus x1 minus x2 to power x2 into x1 square plus x2 square. In this case, your coefficient matrix of the linearized system has 0 real part, and here we have seen that the solution is asymptotically stable. But if we just perturbed our system of differential equation like this, that dx1 by dt equal to x2 plus x1 to x1 square plus x2 square and dx2 by dt equal to minus x1 minus x2 x1 square plus x2 square. If you look carefully, then the associated linear system is same and the eigenvalues of A is having 0 real part, and in previous question we have shown that the 0 solution is asymptotically stable solution, but in this case your 0 solution, the equilibrium solution x1 t equal to 0 and x2 t equal to 0 is an unstable solution. So, it means that if you are discussing dx by dt equal to Ax plus g of x, where g x satisfying the condition that g0 equal to 0 and gx by norm of x is a continuous function of x and it is vanishes as x equal to 0, then we cannot conclude anything if eigenvalues of A all the eigenvalues are A are non-positive and at least one of the eigenvalues has 0 real part. So, that in that case we cannot conclude anything. Now, let us prove the result for the first two cases, and that is that eigenvalues of A are having negative real part for all the eigenvalues, and if at least one of the eigenvalues have positive real part. So, let us prove in the case of 1 and 2. So, we may observe that any solution x t of 1, here 1 is this x dash equal to a x plus g of x. Here we can say that this any solution of this may be written in the following form, that x t equal to e to power a t x of 0 plus 0 to t e to power a t minus s g of x s d of s. And here we have used the variation of parameter method. In fact, we know that we can write down the solution of x dash equal to a x as say any this is the fundamental matrix x t into that constant function c. So, your x t homogeneous part can be written as x t into c, and then by varying this c we can find out the solution of this, and this is I think we have already discussed in one of the lecture. So, we can say that here taking this fundamental matrix solution x t as e to power a t, we can write down the system of we can write down the solution of x dash equal to a x plus g x as follows, that is it is x t equal to e to power a t into x at 0 plus 0 t e to power a t minus s g of x s d s. And here since we are looking for the asymptotic stability of 0 solution, it means that we are looking at the this 0 solution is a stable solution, and any other solution which start in the neighborhood of a 0 solution will tend to 0 as t tending to infinity. So, this we can prove provided that norm of x t is tending to 0 as t tending to infinity can be proved. So, our focus is to prove that the norm of x t is tending to 0 as t tending to infinity. Okay. Now, as we have observed in the case that if all the eigenvalues of A have negative real part, then we can find out a constant k and alpha in a way such that this e to power norm of e to power a t is bounded by k e to power minus alpha t. So, that we have already discussed in previous few lectures. Now, here using this, let us find out the upper bound of norm of e to power a t into x of 0, which is nothing but less than or equal to norm of e to power a t into norm of x 0. Norm of e to power a t is bounded by k e to power minus alpha t. So, we can say that norm of e to power a t into x 0 is less than or equal to k e to power minus alpha t norm of x 0. Now, once we have this, now let us look at, because here if we have two term, one term is here, another term is inside. So, this can be bounded by k e to power minus alpha t norm of x 0. Now, look at the inner integrand, basically e to power a t minus s g of x s. Here to find here in a similar way we can say that norm of e to power a t minus s g of x s is less than or equal to k e to power minus alpha t minus s norm of g of x s. So, here we have shown we have found the upper bound here. Now, still it is not sufficient because it is quite difficult to say simplify this expression 4. So, here we also use the following thing, that we can find a positive constant beta such that norm of g x is less than or equal to some constant into norm of x, and if norm of x is less than beta, and this follows from the fact that this g x upon norm of x is continuous and vanishes at x equal to 0. So, how we can obtain this? If you look at the continuity of g x by norm of x, so we can simply say that norm of g of x upon norm of x minus 0, because it is vanishing at 0, is less than epsilon whenever. So, continuity says that for every epsilon greater than 0 they exist a delta greater than 0 such that this quantity is less than epsilon whenever norm of x is less than delta. So, and this is what this I can write it gx upon norm of x is less than epsilon. So, now for this particular problem let us choose epsilon as alpha by 2k. We will see that why this alpha by 2k have taken. You can take any constant, later on we can fix that. Now, this delta let us say call it beta here. So, we say that since gx by norm of x is a continuous function and continuous function for norm of x. So, a continuous function of x and it is tending to 0 as x is tending to 0. So, with the help of this we can say that norm of gx is less than or equal to alpha by 2k into norm of x, provided that norm of x is less than or equal to beta here. So, corresponding to alpha by 2k we can find out delta and let us call that delta as beta. So, it means that using continuity we can write that norm of gx is less than or equal to alpha by 2k into norm of x if norm of x is less than or equal to some beta. Now, that beta is depending on this alpha by 2k here. Now, once we have all these things, then we can look at our solution, that is norm of xt less than or equal to norm of e to power at x 0 plus 0 to t norm of e to power at minus s g of xs ds. Now, this quantity is less than k e to power minus alpha t into norm of x 0 plus 0 to t. Now, this is less than or equal to e to power minus alpha t minus s. Now, this norm of g of x of s is less than alpha by 2 into norm of x. Now, that 1 k, like here it is e to power a t minus s is bounded by k e to power minus alpha t minus s. Now, and norm of g of x of s is bounded by alpha by 2 k norm of x of s. So, this k will be cancelled out here and you will get alpha by 2 0 t e to power minus alpha t minus s norm of x s d of s. Now, here this inequality will be true provided that norm of x is less than or equal to beta, where s is lying between 0 to t here, because s is lying between 0 to t here. So, if we further simplify, in fact we can multiply on both the side by e to power alpha t, and then we can have e to power alpha t norm of x t is less than or equal to k times norm of x 0 plus alpha by 2 0 t e to power alpha s norm of x s ds here. So, this we can further simplify by taking z t equal to e to power alpha t into norm of x t, and then we can write it z t is less than or equal to k times norm of x 0 plus alpha by 2 0 t z of s ds here. So, here we want to find out the bound on z of t here. So, here we have two ways, either you use directly the ground Wallace inequality if you know, otherwise we can solve this by taking, say, let us say u t as say alpha by 2 0 to t z of s d of s here. So, the only thing is that we cannot solve for z t by just differentiating it, because differentiation of the inequality may not be preserved here. So, to solve this we let us assume that u t equal to alpha by 2 0 t z of s d of s, then we can write down u dash t is equal to alpha by 2 here and it is z of t here. So, we can say that we already know that z t is less than or equal to this quantity. So, we can write u dash t equal to alpha by 2, z t is less than this quantity. So, it is k of norm of x 0 and plus now alpha by 2. Now, this quantity is what? This quantity is your u t. So, let me write it here. So, this is what u dash t minus alpha by 2 u of t is this is I think this is less than or equal to, this is less than or equal to. So, this is less than or equal to alpha by 2 k times norm of x of 0 here. So, what we have done here, we just assume this quantity as u of t, and then we have evaluated the derivative of this, that is u dash t equal to alpha by 2 z t. Now, z t we know that the upper bound of z t is what? Z t is bounded by k times norm of x of 0 plus this is ut here. So, now using the bound of zt, I can write down u dash t is less than or equal to alpha by 2 k times norm of x 0 plus alpha by 2 norm plus alpha by 2 u of t. So, we can write down u dash t minus alpha by 2 u t is less than or equal to alpha by 2 k times norm of x 0. Now, here this we can solve in terms of ut here. For that we simply multiply by e to power alpha t by 2 here. If you multiply here, then I can write this as d by dt of this is what let us say minus sign here, then this will give you what e to power minus alpha t by 2 ut. This if you differentiate this, what you will get this ut and differentiation of this will be what e to power minus alpha t by 2 into minus alpha by 2, and if you take this as e to power minus alpha t and ut, now this is less than or equal to alpha by 2 k times norm of x 0 into e to power minus alpha t by 2. So, what we have done, we multiply by e to power minus alpha t by 2, then this left hand side is reduced to d by dt of e to power minus alpha t by 2 ut, and the right hand side we have written alpha by 2 k times norm of x 0 e to power minus alpha t by 2 here. Now, let us we are solving this d by dt of e to power minus alpha t by 2 u of t, which is less than or equal to alpha by 2 k times norm of x 0 e to power minus alpha t by 2, and this we can solve as follows. We can write down d by dt of e to power minus alpha t by 2 u of t less than or equal to e to power minus alpha t by 2 alpha by 2 k times norm of x 0 here. Now, this we can take it in left hand side, and we can write d by dt e to power minus alpha t by 2 ut minus alpha by 2 e to power minus alpha t by 2 into k times norm of x 0 is less than or equal to 0 here. Now, this part I can write as d by dt of e to power minus alpha t by 2 times k times norm of x 0. So, using this we can write down this as d by dt e to power minus alpha t by 2 ut plus k times norm of x 0 less than or equal to 0 here. Now, we simply integrate with respect to t from 0 to t. So, we have e to power minus alpha t by 2 ut plus k times norm of x 0 less than or equal to putting the value 0 here, then e to power minus alpha 0 by 2 is simply 1, it is u 0 plus k times norm of x 0. Now, what is u 0 here? So, u 0 you can simply find out using this, that ut equal to alpha by 2 0 to t z s ds. Now, if you put t equal to 0 here, then this integral will vanish, this whole thing will vanish, and you can get the value of u 0 equal to 0 here. So, we can get that e to power minus alpha t by 2 ut plus k of x 0 is given by, this is simply 0, k times norm of x 0. So, here we can get the value of ut, that ut plus k times norm of x 0 is less than or equal to e to power alpha t by 2 k times norm of x 0. And if you look at, this is the bound of zt. So, zt is bounded by e to power alpha t by 2 k times norm of x 0. So, that is what we have obtained from zt here, that zt is bounded by e to power alpha t by 2 k times norm of x 0. So, we can say that from this inequality, if we solve, we can get that zt is less than or equal to e to power alpha t by 2 k times norm of x 0 here. So, that is what we have achieved here, e to power alpha t by 2 k times norm of x 0. Now, what is x t here? So, from this we can find out x t is e to power minus alpha t into z t here. So, norm of x t is equal to e to power minus alpha t into norm of z t, and that we can write it here, that k times norm of x 0 e to power minus alpha t by 2 you will get, provided that norm of x s is less than or equal to beta, where s is lying between 0 to t. So, we can say that from this we can write it here, that if so what we have achieved here, let me write it here, that norm of x t is less than or equal to k times norm of x 0 e to the power minus alpha t by 2, provided that norm of x s is less than or equal to beta, where s is lying between 0 to t. Now, here now our claim is that this will be automatically true if we assume that x of 0 is less than some quantity. Now, here we can say that e to the power minus alpha t by 2 is basically less than 1. So, we can say that norm of x t is less than or equal to k times norm of x 0. So, if we choose our x 0 suitably, then your x of t will be less than x of s will be less than beta for s lying between 0 to t here. So, it means that if I choose that norm of x 0 is less than beta by k, then we can say that norm of x t is less than or equal to, here we have written it is k times x of 0. So, it is k times norm of x of 0 here. So, we simply say that if x 0 is less than beta by k, then you can say that norm of x t is less than or equal to beta here, beta times norm of beta. So, if x of norm of x 0 is less than beta by k, then your norm of x t is less than or equal to beta for all t greater than or equal to 0 here. So, it means that the previous this inequality is always true for all t greater than or equal to 0 here. So, it means that the restriction that norm of x is less than or equal to beta can be relaxed, can be met if we assume that norm of x 0 is less than or equal to beta by k, because in this case norm of x t is always less than or equal to beta for t greater than or equal to 0. So, this condition is now met automatically, that norm of x is less than or equal to beta. So, this if you say that norm of x 0 is less than or equal to beta by k, then norm of x of t is less than or equal to k times norm of x 0 into e to the power k times norm of x 0 e to the power minus alpha t by 2. So, here this inequality is always true for all t greater than or equal to 0 if x of norm of x 0 is less than beta by k. So, finally, we observe that norm of x t is less than or equal to k times norm of x 0 e to the power minus alpha t by 2, and then we can say that norm of x t is tending to 0 as t tending to infinity, and hence we can say that the equilibrium solution x t equal to 0 is asymptotically stable solution. So, so this says that it is a stable solution, and then because of e to the power minus alpha t by 2 term is here, as t tending to infinity, this term will vanish to will tend to 0 very fast, and we can say that x t will tend to 0 as t tending to infinity, and hence we can say that x t ideally equal to 0 is an asymptotically stable solution. So, what we have proved that if eigenvalues of A, if all the eigenvalues of A have negative real part, then the solution, 0 solution of x dash equal to Ax plus Gx is asymptotically stable solution. Now, here regarding the proof of B, this proof is quite lengthy and involving. So, here we can assume the proof without proving it here, and so it means in this way we can say that we have considered all the cases, case A, case B and case C here. So, now with this we have completed the theorem. Now, let us consider the application here. So, in this proof we have just discuss the stability of equilibrium solution which is ideally equal to 0. Now, how we can utilize this theorem to discuss the stability of non-zero equilibrium solution, that we are going to discuss in next few slides. So, now we say that this theorem 1 is also useful in determining the stability of equilibrium solution of arbitrary autonomous differential equation. So, let x naught be an equilibrium solution of the differential equation dx by dt equal to f of x. Now, this x naught may not be 0. If it is 0, we have the result we can get it. But if x naught is non-zero, let us see how we can say utilize our theorem 1 to discuss the stability of equilibrium solution here. So, now we simply shift our origin and we simply write zt as xt minus x naught here. So, using this, now I can write z dash t is equal to x dash t minus since x naught is a equilibrium solution. So, x naught dash is simply 0. So, z dash t equal to x dash t. Now, z dash t equal to we can simply write dx by dt, and dx by dt is already given as f of x. Now, x can be replaced as zt plus x naught. So, we can say that now we can have z dash t equal to f of x 0 plus z here. Now, what is the change in equation number 5 and this equation number 6 here, that here your equilibrium solution of 5 is x naught. It means that f of x naught is equal to 0 here. But if you look at the system 6, here if you say that z equal to 0 is an equilibrium solution here, because when you put z ideally equal to 0, then it is nothing but f of x naught, and we know that it is 0. So, it means that we are able to convert a problem where we have a non-zero equilibrium solution to a problem where we have 0 is an equilibrium solution here. So, this is now converted into z dash t equal to f of x naught plus z. Now, we can say that here this can be converted into a form which we have discussed earlier, that is z dash t. We want that if we impose certain condition on f here, then this f of x naught plus z may be written as a of z plus some g of z, where a z is a linear part in z and z z is something that g of 0 equal to 0 and g z upon z is a continuous function of 0 and vanishes at z equal to 0. So, we need to find out a condition on f such that we may write it like this. So, here let me write it here, that clearly z t equal to 0 is an equilibrium solution of 6 and the stability of x t ideally equal to x naught is equivalent to the stability of z t ideally equal to 0 here. So, here we have the following lemma by which we can say that we can write down the expression f of x naught plus z as f of x naught plus a z plus g z here, where g z satisfy the property mentioned in the previous theorem, that is z z divided by norm of z is a continuous function of z and vanishes for z equal to 0 here. So, the condition we are putting on f is the following, that let f x have two continuous partial derivative with respect to each of its variable x1 to xn, then f of x naught plus z may be rewritten as f of x naught plus z equal to f of x naught plus a z plus g of z here. Now, I am giving you these are the sufficient condition we impose on f here. Here we may consider only that this thing, that first order partial derivative exists and second continuous and second order partial derivative simply exists, then also we can write down f of x naught plus z equal to f of x naught plus a z plus z z here. The following lemma, this lemma has several proof. We are just using one result. We simply here we have written z dash t equal to f of x naught plus z here. Now, we already know that this f of x naught is equal to 0 here. So, I can write this as f of x naught here, right. Now, since f of x naught plus z minus f of x naught, then using your mean value theorem, I can write this as f of x naught plus some theta z here, where theta is lying between 0 and 1 here. And so, here now so this can be written as z dash t equal to f of x naught plus theta z. Now, here we are assuming sorry, it is with respect to the derivative with respect to x here. Now, sorry, it is a function of z. So, f z x naught plus theta z, it is given here. Now, we have assumed that this has continuous partial derivative. So, it means that this implies that let limit theta tending to 0, your f z x 0 plus theta z is nothing but f z of x naught here. Sorry, it is z tending to 0. So, limit z tending to 0, f z x naught plus theta z is equal to f z x naught, or I can write here f z x naught plus theta z equal to f z x naught into z minus plus some g z here. Now, this implies that g z is tending to 0. So, this implies that limit z z is tending to 0 as z z upon z is tending to 0 as z is tending to 0 here. So, this is one way to look at the say proof of this. Another way to write down the proof is using Taylor's theorem. Then since f is what? F is f x naught plus z is nothing but we can write it f1 say f1 x naught plus z, f2 x naught plus z here, and fn x naught plus z here. Now, for each fi we can write down say fi x naught plus z as your f of fi x naught plus, now here we can write down z1 dever f1 dever fi upon dever z1 plus so on zn dever fi dever zn plus the higher order term. Now, this is nothing but okay, and similarly we can write down for each I equal to 1 to n here. So, it means that I can write down, let me write it here, that for each I fi x naught plus z is given as fi x naught plus your z1 dever fi dever z1 plus z2 dever fi dever z2 and so on zn dever fi dever zn plus higher order term. So, this I can write it for each I equal to 1 to say n. So, we can simply say that in particular I can write f of x naught plus z as this is f1 x naught to say fn x naught plus, now this let me write it here, this is what dever f1 dever z1 to dever f1 dever zn and to dever fn dever z1 to dever fn dever zn multiplied by z1 to zn here plus higher order term. Now, higher order term means involving the say square terms of z1 z2 and zn's and multiple of this. So, it means that here your zz will be containing say polynomials in terms of zi's of degree more than 2 here. So, this means that this is your f of x naught here, this we denote as a and this is z plus whatever left is your gz here. Now, gz contained say polynomial terms in terms of z1 to zn of degree 2 or more here. So, this is what we have written here x naught plus z, I can write it like this. So, that is what is given here, that if fx have two continuous second order continuous partial derivative with respect to each of its variable x1 to xn, then f of x naught plus z may be written as f of x naught plus z equal to f of x naught plus az plus gz here. So, here we are not assuming anything on any condition on x naught, but if we assume that f of x naught equal to 0, then we can do it by say mean value theorem also and the continuity properties here. But here in general if fx fx contain the second order fx has a second order continuous partial derivative, then we can rewrite f of x naught plus z as f of x naught plus az plus zz here. Now, since f of x naught is 0, then I can write this the previous problem z dash equal to f x naught plus z as az plus gz, where gz contains the term in terms of z1 to zn with power 2 or higher. So, so here we can rewrite, we can apply our theorem 1 for general nonlinear system also, where we want to check the stability of an equilibrium solution x naught here. So, with this we finish our lecture here, and next lecture we will discuss some example based on this observation, and discuss the stability of an arbitrary equilibrium solution that we discuss in next lecture. Thank you very much for listening us. Thank you.